Anyway, we're going to have a review actually on chapter 16. Today it's called the summary 16. So there are all kinds of problems listed here. So we look at, let's look at the table. So there are how many theorems here mentioned here? Just 1, 2, 3, 4, 5. And those are the 5 theorems. The first one is called the fundamental theorem of calculus. Yeah, first of all, we have a definition for the line integral and the surface integral, right? And the line integral, surface integral, then those are just, you have to use parameterization to evaluate them directly. But in some cases, we can change the integral to another integral, like a line integral to double integral, or the double integral to the line integral, and then you can evaluate quickly. Okay, so let's recall the theorem called fundamental theorem of calculus. So if you, let's compare. This is the difference at the two endpoints. Okay, this is called fundamental theorem of calculus. And then this can be generalized, slightly generalized to the line integral. If this is a line integral C, right, and they have a vector field along this curve, okay, but that's vector field, it's a special vector field, it's called the gradient of some function. Then the line, then the integral, the line integral of the gradient f at times, I think I should use a TDS. I prefer that one because then I don't need to mention the parameterization of the curve C. Okay, so T is the tangent of the vector. Okay, and this one, if this point is going to be P, that point is Q, and that just is the difference of the values of those two endpoints. Very similar to the above one, but now it's not the integral around the integral around the interval. Okay, it's the integral around the curve. I think the special case will be the above one. So fundamental theorem calculus. But we can prove that using fundamental calculus to prove there's a fundamental theorem for the line integrals. Okay, this is still the one dimension. Okay, so in the future, if you can figure out a vector field is conservative, then you have two options: either to evaluate this line integral directly, or you can use this formula and then much quicker. Okay, as long as you find the function. Okay, so for example, let's look at this sum. Okay, so if in case if f is conservative, okay, then you can evaluate this integral, okay, by the above formula. You don't need to find parameterization for the curve and use the integral with respect to t, for example. Okay, so that you have two options. One is you can find the f, little f. So then you just evaluate the little f at the two endpoints of the curve. Then you take a difference, or you can directly to evaluate, and this is going to be a parameterization of a t, right? T is between a and the b. Then use that. What is this one? This is going to be integral from a to b. right? Capital F, gamma T, and times dt. Okay. All right. So that's it. Now, what is this part? This is nothing but T and the ds. Okay. T is a unit normal tangent vector. ds is the product is going to be give you this. Okay. Actually, T is going to be R prime T. You normalize it. Okay? And but ds is going to be this one. Right. So the product, you know, the normal, the length of the tangent vector, the length of the R prime T is cancelled out. Okay. So that's why you end up with that. Okay. So you have two options. If you forget or don't recognize this is a conservative, the vector field, then you have to use a parameterization to evaluate. Okay. Use this formula below that. Now, if sometimes it's quicker to find a little function f so that the vector field is gradient of f, then in that case, you once you find the little f, you can quickly evaluate this line integral. Okay, so let's look for some problem from the book. All right, so here's a good example. So you are given x, y, z, which is going to be e to the y I plus x e to the y plus e to the zj and plus y e to the zk. Right? Right. So this is a vector field, and C is going to be line segment from the point 0 to 0. Now sometimes it's not a line segment, sometimes a curve like that, you know, passing through those 2 points. Then it's more complicated. You have to find the parameterization for the C. Because even the line integral, you still have to find the parameterization, right? Now the point is how to, because this one is already tell you that F is a conservative. Now, if you are not told F is conservative, you have to take a few seconds to think about how to check F is conservative. Okay, that's another question. How to check if F is conservative? This is a vector field in 3-dimensional space. Remember, the theorem is a function defined in the whole 3-dimensional space, and if the curve of the vector field is 0, then this is conservative. Okay, yeah. So we assume that this is conservative. Okay, we are told that. Okay, we are given that F is conservative, so you don't need to verify. But later on, I'm going to, yeah. So we are given the information that F is conservative. So you already told that. Okay, in this case, save you time to even actually give us a hint also. You know, you're going to use, you're going to find a little f first, then you can avoid to evaluate the integral, line integral, okay? You can just find a little f, so the capital F is going to be gradient of a little f, then you evaluate that to end point. So you don't need to even find the parameterization for the line segment, right? Save you time. So let's try to do that. F is going to gradient of little f, right? So what does it mean? That means the partial derivative of this is going to be e to the y. The partial derivative of this is going to be x e to the y plus e to the z. Okay, so we hope we can find this little f. Right, so there are 3 equations here. And how can I integrate the first equation with respect to x, okay? So you view a fixed yz. So this side is going to be just, just f, okay? fxyz. So I'm not going to waste time to write down the component. So this is going to be e to the y is a constant with respect to x. So e to the y plus x, right, times x, plus a constant. But this constant, remember, depends on y and z, okay? Yeah, we fix y, z, so you can evaluate. Then you differentiate, plug into the second equation. So you got, and then you differentiate with respect to y is e to the y times x, and right. So let's forget yz here. Okay. So this is supposed to be x times e to the y plus e to the z. So in other words, I'm going to solve this equation. Right? Not too bad, right? Yeah. Then you integrate with respect to y, and the same story here. This is a c, the other side e to the z y plus, let's call it k, but k depends on z, okay? Because this time c is a function of yz, and you integrate with respect to y, then you're by fixing z. So the constant actually depends on each fixed z. So now, first equation, second equation are satisfied, then you just need to look at the last equation. The last equation says that, okay, so the last equation, when you differentiate f, so what I'm supposed to get? So when you differentiate f, you see, what is a c, right? C here is, what is f? This is f, and c is e to the zy, and times y, right? Plus k of z, right? After put them. This is my f, okay? This is a c, okay? All right, so when I differentiate, the first term is 0, the second term e to the z times y, the third term is this. Then I go back to what I'm given here is partial derivative of y with respect to z. So y e to the z is y e to the z, and then clearly k must be constant. Right, it's going to be 0. Right, so my f is going to e to the yx, e to the zy plus any constant. Okay, then so now the line integral, yeah, c. Okay, this line integral, since it is going to be written in this form, right? Then according to the formula, it's going to be the difference at the two end point. Okay, the difference at two end point, and this is going to be the 403. The other one is 020. Okay, yes, the difference at two end point. So this is a curve here, and that's 2 points, 403, and this point 020. Okay, we go in that direction. I draw the curve actually a straight line. Yeah, let me draw the straight. So sometimes you're given very bad curve, Yeah. So then you just evaluate, right? So 40y, when y is 0, the first one is e to the 0, be careful, and the 4 plus z is 3, and the y is 0, right? Minus, when x is 0, e to the 2 times 0, plus e to 0, y is 2. Yeah, be careful about this number. Okay, so the first term is 4, the second term is going to be 2, so the answer is 2. Right. But I just said that if you do not recognize f is conservative, and if you do not go their way, and what we should do? Okay, I'm just going to set up the integral for you, but I'm not going to evaluate. The answer should be still 2, right? So how to do that? If you want to evaluate this line integral, first of all, you have to find the parameterization. Okay. If we don't know f is conservative, okay, how to evaluate this integral, right? How to evaluate this line integral? Okay, this is Ts dt, right? So you have to do that directly. So using the formula, parameterization, the line, how to write down the parameterization for the line segment. This will be the starting point times t, the vector. Vector is the difference of the two vector, the difference of those 2 points. So it's 4 minus 0 is still 4, 0 minus 2 negative 2, 0 minus 3 minus 0 is 3. Okay, so this is, you can double check that t is between 0 and 1, and when t equals 0, you get the starting, you get the point 0, 2, 0, and when t equals 1, you get another point 4, 0, 3. Okay, so this is a parameterization. It's not too bad, right? And so if you want to write down what is x, x is going to be 0 plus 4t, right? Y is going to be 2 plus negative 2t, and z is going to be 0 plus 3t. Not too bad, okay? So this is a parameterization for the line segment. And so this c f dot t ds is going to be the integral from 0 to 1 and x, y, z times r prime t dt. Maybe it's not that complicated, okay? So you have to you have to x, y, z, right? What is a vector? E to the y, right? I plus, well, x 4t e to the y, y is 2 minus 2t. It's complicated. And e to the z, that's a j, plus y, 2 minus 2t, and e to the z and 3t. Okay, and then the product, the derivative of this is going to be 4, negative 2, and 3, and dt. And then you multiply this out, okay? You can 4i negative 2. So the answer will be 4e to the 2 minus 2t minus 2 plus 3. I think it will take too much time to evaluate this integral. Almost nobody can get right answer at the end. There'll be integration of odds, and see that. Okay, so the point is that when you get to this point, you have to think about, okay, maybe the function is conservative because otherwise, it takes half hour to finish the computation. So at this point, you really shouldn't continue. Either leave it here and move on to the next problem, because if you cannot finish the last problem, 10 points, this one, if you stop here, maybe I take 3 points off if you cannot evaluate, right? Compared to the 10 points, you should spend more time on another problem if you have no clue what is next step, because there's an integral. This is this is just a regular integral, right? And of course, when you do that, you have to simplify a little bit. But you still have a e to the 3t, e to the 2 minus 2t, yeah, it's complicated, okay? But if you have a software, MATLAB, and type the function, you can get answer quickly, just 2. When at the moment when you finish typing, then you already get an answer. Okay, so we stop here. It's not a good idea to waste time to evaluate this. Okay. Now then we move on. Then we move on to the next theorem. We know that. Let's go back to the integral. Right. We evaluate the 2 endpoints. This is a fundamental theorem of calculus. Okay. So this is talking about just a line integral, right? It's a interval. No, there's a. I just want to draw a one coordinate line. Okay. So the function is defined on this interval from A to B, and this function is a derivative already. Okay. Now, how to generalize to the coordinate line is a flat strict line. So the coordinate, one coordinate line can be generalized 2 coordinate lines perpendicular to each other. Okay, so now you have this. Okay, but then the problem is that an interval in a 2-dimensional space is not going to be a rectangular box. It could be a general domain D. Okay, it's more complicated, more freedom there. Okay, so when I say here's a domain on the x-axis, then as long as the domain is connected, it's just only one interval. But when you say domain in the xy plane, if it's connected, then you cannot control the boundary. Okay, so this is a D. Okay, so the boundary is denoted by the bound. This is notation boundary. Okay, and this is going to be denoted by C. It's going that direction, have an orientation. So if I have a vector now, how can I generalize that theorem? So Green did it. The Green did it that in 2-dimensional case, I have 2 functions, P and the Q, okay? And then I'm going to call the F. Okay. You don't even need to mention the vector field, just 2 functions. You need 2 functions instead of 1. So he says that compared to this above theorem, right? So now you have a double integral, and the qx minus py, and dA is going to be the integral around the boundary. And this time is a little bit complicated. It's actually c p dx plus q dy. Okay, so that's the theorem. Yes. This is a generalization of the above fundamental theorem. Okay, in 2-dimensional. So the endpoints here now is the boundary of the domain. Okay. Okay. So you see, on the left-hand side is q sub x, p sub y. Those are partial derivatives. On the right-hand side, there's no derivative, p and q. Okay. Since it's 1-dimensional, so you still have to integrate it. So dx dy there. Okay. So this is a generalized from 1 dimension to 2 dimension. Okay. But this time when we use the theorem is we actually do the opposite way. For the fundamental theorem calculus, we evaluate the integral and at the end then change the integral to the difference of the function at the 2 endpoints. But here we go do the opposite, go the opposite direction. We try to evaluate the line integral, then change it to the double integral. Okay, it's harder to now given double integral. It's harder to tell whether this is a q sub x, qx, q, and py. Okay, but in calculus 1, we know that we always trying to express the function as a derivative of some function. Then we can evaluate the integral. But here, if you are given a double integral, right? How do you see whether f is going to be this for some P and the Q, and this is a very difficult problem. Okay, so given a double integral, you are not going to use a green theorem to evaluate. You actually do the opposite, because it's difficult to find the Q and the P, so that the difference of partial derivatives is going to be F. Right? It's almost impossible. So we're not going to use the green theorem to evaluate double integral. We're going to use the green theorem to evaluate the line integral. Okay, we do the opposite way. And here, for this theorem, I can call green theorem also in dimension one. Okay, it's a fundamental theorem of calculus. For this one, we use that to evaluate the integral. We evaluate this integral. Okay, so we have to find out some function so that f prime x equals fx. So we always try to find anti-derivatives, right? So this procedure, right? So it's very useful theorem. If we're given an integral and f, and if we're able to find anti-derivative, then just evaluate the integral. But here, if you're given if you give a double integral f, can you find the anti-derivative of a little f, right? You need a two, q and the p, and that's nobody tell you how to do it. It's hard. Okay, so we never try this. Okay. So, but the green theorem is still useful when we try to evaluate the line integrals. Right. So here's an exercise. Okay. Evaluate this line integral. Okay, where C consists of the parabola y equals x squared from -1, 1 to positive 1. And the line segment from 1 to 1 to -1 positive. Okay, so we're going to draw the picture here. So this is in two-dimensional x-axis to y-axis. Okay, so -1 and 1 is here, and the 1 and the 1 is here. So it's going. This is a parabola. Okay, and then line segment from 1 to this thing. Okay, so this is a curve. See, we're trying to find. We're trying to evaluate this line integral. Now this where is the function? Okay, it's y squared. Okay, x. X squared. All right, so the meaning okay, we can the line integral can be also described the following. So c xy squared dx x squared y dy. Okay, this is actually the integral of f dot t dx. Okay, and what is f? F is going to be xy squared negative x squared y. Okay. And somehow TDS can be written in the form like dt dy. So the dot product gives you the above expression. Why this is true? Okay, so why this is true? Okay, let's understand this is about last identity. Okay, so if x equals x of t, y equals y of t, right? Then t ds is going to be what? Is going to be the derivative. T is going to be this, and the ds is going to be x prime t squared plus y prime t squared dt. That's the ds. That's the t. So when you multiply this out, and you just get x prime t, y prime t, and dt. Okay. So when you move in dt, you get this. But that is just dx and dy. Okay. Yeah, that's okay. Just trying to explain. So anyway, the above one is a line integral, and if we want to integrate this line integral, as long as the curve is closed, okay, then you should think about to use green theorem to solve the problem. Otherwise, it will be very complicated. You have to pretty much, sometimes it's not a circle like this one consists of two pieces. For each of them, you have to find a parameterization, right? Right, and then you have to evaluate this line integral. Evaluate this line integral. Okay, for each parameterization. I think it's very complicated. So the best way to do is to consider this domain enclosed by the curve, right? And use the green theorem to solve the problem. Okay, so use the green theorem. Using green theorem, we can easily evaluate this line integral, and actually it becomes a double integral. And what is q, right? It's going to be qx minus py dA. So our q is going to be negative x squared y. P is xy squared. Okay, let's simplify it. We will get negative 2xy here, negative 2xy here. Okay, so just negative 4xy. Right. Now, the next step is just evaluate double integral. The question how to evaluate. You can put the x outside, dx outside, you can put dy outside. Really doesn't matter. But the best way to do is you have to choose x first and look at this horizontal line sigma. Okay. So x should be outside. Then for each fixed x, then you look at the y value. Okay, the y value changes from the top one is 1. The bottom one will be y equals x squared. This is because from the parabola. So it's x squared, negative 4xy dy. Okay. So the antiderivative is going to be negative 2xy squared. Be careful. This is 4x is constant here, constant times y. So the antiderivative will be half of the constant times y squared, right? So that's just 1 minus this plus x squared and the square. All right, the antiderivative, this will be negative x squared. And this will be, what is that? X to the fourth, x to the fifth. So 2 over 6, x to the 6. I think it's going to be 0. It is going to be 0. And why it's going to be 0, right? Because this is the other function. Evaluate over symmetric interval. It's going to be 0. Now that also indicates the vector field might be conservative. Oh yeah, this is integral. No. This is the integral of the function which changes signs over. You see, negative 4xy. Look at this. This is the domain is symmetric. Okay, the domain is symmetric, but the 4xy symmetric about the y-axis. Okay, and you look at the fixed y, x changes signs on both sides. So that's why negative part, positive part dash that we cancel out. Okay, so it's going to be 0. Okay. So now we're going to continue to generalize the theorem. Okay, there are two. Okay, remember the integral along the interval, right? This is a fundamental theorem. I'll keep writing this, and this is generalized to the green theorem. Okay, so that's a D. Okay, and the integral, double integral here on both sides, qx minus p sub y dA is going to be becomes a line integral. It's a p dx plus q dy. So, but on the other hand, I generalize this integral to the line integral, right? Okay, that's a C. So what do we have here is, what do we have here? Remember, if this is a C, right, the interval now is a strict line segment, becomes a curve in the space. And this is going to be the difference at the two end point, which is going to be fq minus f of p. Right? So I can also make this flat domain be a surface. Right? It's going that direction. It's keep the same dimension. Okay? The line, the integral along the sigma along the interval becomes the integral along the curve. And here in two dimensions, this is an integral, double integral over domain, flat domain. And I can also generalize to the problem. This is in any dimension. Okay, let's just assume it's in 3 dimensions. So the surface, it could be a curved surface. Okay, and then that's a D. Okay, I call it S maybe. That's the boundary of S is a curve. Okay, so this is a flat, and here's a curve. All right, so we are going to generalize this green theorem to the other side. Okay, so what we can get here is this is a vector field F in the space, and we have the following theorem: the double integral, the surface integral, and here's the curve of the vector field F and times and actually times ds. Okay, and this is going to be the line integral f times t ds. Okay, so it is going to be, yeah, this is actually the generalization of the green theorem. Okay. Yeah, I'm going to change a little bit here. Actually, I want to use n and ds. Okay, better. Yeah. All right, so let's compare these two, green theorem and this is called a Stokes theorem. So this is actually is going to be, if in this case, if you write f in the form p and the q, okay, then if you view it in three-dimensional space, this is just equal to double integral curl of the vector field times the k, okay, and the dA. So there's a flat dA just equal ds, and this is going to be the line integral and f t ds. Okay, so you can view the green theorem as a special case of the Stokes theorem. That's it. Okay, so now let's take a look at another example. How do we apply the Stokes theorem? We usually you see, you can also use a line integral, right? You've had a line integral, but there's so many surfaces here are enclosed by the curve, given curve. So so we don't have so many examples to exercise to do here. You see, you can, yeah, to apply the Stokes theorem, there are two different type of problems. More likely, you're going to give a line integral, but the line integral is not like a closed curve in the space in the xy plane. It is curved. Then the question is how to evaluate this line integral. And maybe you can change it to the surface integral. But surface integral is still not as simple. Okay, and okay, let me then, yeah, there are a few choices here. Okay, so let's try this. Let's try the following. Try the following. Problem number 32. All right. Here's a good question. All right. So here's C is okay. C is a circle which is the intersection of the sphere The sphere is x squared plus y squared plus z squared equals 5. And the plane z equals 1. Right? And F is going to be the vector field. X squared y z squared, and z cubed e to the xy. Right? So you have a vector field. Okay. Evaluate the line integral f dot ts ds along this curve. Okay. This is of course, C is oriented in. I have to mention that how does it look like, right? Orientation. So this is a picture of the sphere. So I'm talking about this curve. It's oriented in that direction. Right? That's a C. Right. So this is Z equals 1. Right. So we can actually, since already you are given the circle by this way, it's actually intersection of surface and the plane. So you can evaluate this line integral using Stokes theorem. Change it to the line integral to a surface integral, not the double integral. Okay, if it, yeah, you can change it to the double integral, but the surface still there. You can use that portion, the S. Okay, it's enclosed by circle, and let's try to use a surface integral instead of. Okay, so we can do like that. So by the Stokes theorem, this is going to be the surface integral curl of f and ds. This is a end. Okay, we point in that direction. Okay, ds. So let's find the curl of the vector field first. Maybe that's easier to do using this, just similar to the application of a Green's theorem. Okay, the curl of the vector field is going to be ijk partial derivative x, partial derivative y, partial derivative z. And x squared yz squared, and z cubed e to the xy. Whoa, it's too bad. Very complicated. I hope I can complete the computation without mistakes. All right, so what is I? Yeah, let's put I here. So partial derivative of this is going to be x z cubed e to the x times y minus 2yz, okay, plus, it's actually minus, yeah, so that's j. And that partial derivative z cubed, when you differentiate with respect to x, you get a y minus x squared y, okay? And then k. So that is going to be 0 minus x squared z. Okay, well, it's too bad. I'm not sure we're able to simplify that. Okay? So the normal vector is going to be x, y, z. So we can multiply this out first. Okay, the curl of the vector field times this. Right, that's going to be x squared z cubed e to the xy minus 2xyz. Right, and then minus y squared z cubed plus x squared y squared, and minus x squared z squared. That's ridiculous. Okay, so yeah, it's not going to be simplified. Okay, so that means this line integral, yes, it becomes a surface integral of this function over the portion of the sphere. Okay, so this line integral becomes the surface integral. This is a portion of the sphere. It is going to be x squared z e to the xy, and you still have to replace z. It's on the sphere. So I can evaluate this, too complicated, right? You have to parameter the sphere, then blah, blah, blah. So there's another option. Another option is, why not to use that portion of the sphere, that portion of the surface, the flat piece on the z, on the plane. Because that's also, right? That's a flat one, okay? You don't need to worry about sphere. You evaluate the line integral. But line integral, this curve can be boundary of any surface. And in particular, this is a boundary of this disk. Okay, if you use this, it'll be much easier. So think about this. This is just a circle in the sky, right? And this is z equals 1. If z equals 1, x squared plus y squared is going to be 4, okay? Because 5 minus 1 is 4, because z equals 1. So actually, the points x, y, z is 1, and x, y satisfies this equation. So this is a surface is S. Let's call it the S2, okay? So this can be also, but the S2 is a normal vector. For this case, the normal vector is going to be just K, okay? So the inner product is much simpler, okay? The inner product, for this case, the inner product just only takes the last piece, which is going to be negative x squared z. But the z is always equal 1, so just x, negative x squared, okay? You will see that it will be much simpler, okay? So this line integral is going to be the surface integral on S2. That's the second one. And this can be negative x squared and the ds. But it's a flat surface. ds is just equal to dA. It changes. You can look at this D, domain D. So this is just nothing but the domain D, x squared and dA. Okay, the same. It's a flat. Okay, if you use a Jacobi, and you get same thing, just change it to. If you use a map, right? So parameterize this circle, this disk in the space, and if your parameterization will be the trivial one, okay? And then you can quickly get ds is going to be just equal to dA, okay? So now this is a disk, and use the polar coordinates, you will get I is from 0 to 2, and theta from 0 to 2 pi, and negative x is r cosine theta squared, then r d theta dr, okay? Then not too bad, I can evaluate. Okay. So the antiderivative of cosine square theta is going to be half of 1 plus cosine theta, cosine 2 theta. So the integrate, this part is going to be pi. And here is 1/4, 2 cubes. And that is going to be 1/2 times 2 pi. Right? So the answer is going to be negative 2 pi. Right? So I do use the Stokes theorem to evaluate this line integral. I choose a special surface, okay, for that curve. If I choose a round surface and I get this one, it's very complicated. I have to pretty a sphere, use a sphere coordinates, and I was stupid. I shouldn't use that. I should begin with this, the flat disk. Okay. So if you want to do that directly, you have to wisely choose a surface. If you integrate this line integral directly, can you do that? Yes, but you will see. It's complicated. Okay, z is always equal 1, and along this it's probably okay. Yeah, evaluate this line to just parameterize this curve in the space, and then you can do that problem directly using parameterization. The parameterization, the line integral for the parameterization is going to be x equals that curve, right? X equals 2 cosine theta, y equals 2 sine theta, z is going to be 1. Okay, theta between 0 and 2 pi. Okay, and then the line integral. The line integral becomes, okay, so this line integral CF TDS is going to be the integral 0 to 2 pi and F okay. Yeah, so R theta is given by this. Right. So you just plug into this integral. So F is going to be F. Let's write down what is F. Okay, F is going to be x square. So 2 cosine theta square and y at 2 sine theta. Z is 1. Okay, that's first component. Second component 2 sine theta. Z is 1 square. And the third one, Z is cube e to the product of those 2, 4 sine theta cosine theta. Okay, this is the F. Then negative 2 sine theta and 2 cosine theta is 0 d theta. All right, so when you multiply this out, the last third component is gone because it's 0. So you end up with, wow, 4 times 4, negative 16 cosine square theta, sine square theta, and plus 4 sine theta, cosine theta, and d theta. Okay, so evaluate this integral. I think we can do that. Okay, we should be able. It's not too complicated if you do it directly without using Stokes theorem. All right, so I'm going to move. Okay, this will be 4 2 cosine sine theta, so it's sine 2 theta squared, and that will be 2 sine 2 theta d theta. But integral of sine 2 theta from 0 to 2 pi is going to be 0. Right? So I just needed to integrate this one. If I integrate this one, I need the double integral 1 minus cosine 2 theta is 4 theta. This theta. And finally, the integral cosine 4 theta is going to be 0. So it's negative 2 times 2 pi. It's negative 4 pi. Am I right? I hope I don't make mistakes. Okay. Why there's 4? All right, let me double check. I have no clue where's the mistake. Okay, let me double check the above one. Guys, this is a quarter. Oh, I see. That should be 4. Okay, that's small mistakes. R cubed. The antiderivative is 1/4. The other antiderivative is like this, right? So that's why I'm missing one factor here. It's 4 pi. So that's it. Yeah, good. Same answer. Yeah, mathematics, the theory is always correct. If the answer is wrong, that's my mistake. It's not mathematics. It's not like a biology, I tell you. Because you never see the real truth. When you do the experiment, you find something. But next time, maybe it's different. It's not the same. Okay? But by biologists, you immediately jump to some conclusion, publish papers. Well. So, okay, so now what, right? We going this way, right? Let me, let's try to understand this whole series. So this is a repeater, okay? This is the integral. I keep writing this, okay? Then we forget the curves and the surfaces. Just to look at this generalized to the next one. Green theory becomes okay. The Green theorem says that you have double integral and qx minus py dA is going to be p dx plus q dy. Okay, that's the generalization, the above integral along the interval. Then the interval becomes a domain, flat domain in the two-dimensional plane. Okay? Can we, and this time, so we don't have a single f, we have our f is a vector. Okay? It's going to be p and q. Okay? The derivative of f is not going to be like that. The derivative of f is going to be like this. Okay? It's a combination of those two. Then the values at the end points, we don't have end points, we have the boundary. So you still have to evaluate the integral. Okay? It's become line integral. Okay? This is going to be c, p, and q, and then dx, dy. Okay? It's two-dimensional. Okay? So we can continue, move on to the high-dimensional space. Right? We live in three-dimensional space, so we cannot just focus on two-dimensional plane. So we continue. So let's, right? Just assume everything is flat. So we have so the domain becomes a solid, like a potato, okay, in the space. And then we still have a vector field F here, and it's going to be P, Q, I have 3 components. Can I have a similar thing? Right? Right? After green, and you think about that. Can I find a double, here's a triple integral, and here's a bunch of the partial derivatives of PQR, right? And then this can be, becomes the surface, that's inside is E, and the surface is, boundary of E is going to be surface, and there will be surface integral. The surface integral should be just F. and the ds, I think, right? So normal vector ds, okay, ds, because this one will be I'm going to, right, for the line integral you can only talk about this, right? For the surface integral, you don't have a tangent vector. Tangent vector is not unique. Only the normal vector is unique. So we use a normal vector. Okay? Can we express? Can we find the? Look at the Green theorem, right? Green theorem is like a bunch of derivatives. I can call it curl of f. Okay? Yeah, just introduce notation. Yeah, actually, it's more precise. The curl of f times the normal vector to the plane. Okay. So now we live in three-dimensional space, so we want to establish similar result in three-dimensional case. Okay. Our boundary is a sphere, and the integral of the vector field around the sphere can be only defined in this form, f times f, the dot product f with the normal vector, because for the plane, or for the surface, tangent vector is not unique. But for the curve in three-dimensional space, tangent vector is unique, but the normal vector is not unique. Perpendicular, that's a 3. Only for the curve in the xy plane, the normal vector is almost unique. Just have two choices. So this is a tangent vector, right? T, and then normal vector you have a perpendicular to T, and you have 2. But we don't have a theorem using normal vector, okay? For the curve in two-dimensional. I think you can. That's possible. Let's find that. Okay, later. Yeah. Can you change f to n? Yeah. Okay. Then you really have a similar result, because for the curve in the plane, the normal vector you have two choices. Okay. But the tangent vector, normal vectors, they're related. Okay. But for the solid in three-dimensional space, the tangent vectors are not unique, but the normal vector is unique. Okay. So this is what you're going to get, the divergence of f. Okay. So divergence of f is going to be partial derivative p right? Very simple. So this is not exactly like a generalization of the Green theorem to higher dimension case. I'm going to modify the Green theorem. Then you will see it's the same. Okay, how can I modify it? This is still domain D. So I'm not going to use a tangent vector. I'm going to use a normal vector. How about this? Use a normal vector, point outside, right? Use a normal vector. But the tangent vector, what's the relation between tangent and normal vector? If the tangent vector is going to be, if the tangent vector is going to be A and B, okay, components, this normal vector, okay, point to that direction is going to be B and negative A. Okay, why? Why it's B negative A? Because they're perpendicular to each other. The only question is why negative A here, not negative B, right? So look at the picture here. I'm going to use, this is A and B. How can I describe this vector, right? Component here, just switch it. And the second component will be negative, but the first component is still positive. Okay, so that will be B and then negative A, okay? So that's perpendicular to each other. Okay, so now the line integral C f dot normal vector instead of tangent vector, okay? And this actually is going to be P and the Q, right? Normal vector, I'm going to use a B and the negative A ds. But that once I make them, multiply them out, I will get B, P, A, and the Q, ds, right? I'm going to express that as a product of right? Great. So this is going to be T, okay, instead of F, right? I can change it to that. So now, according to the Green theorem, and that is going to be Px minus, because that's P, okay, by Green theorem, and the negative Q, Y, D, A, okay? And that is nothing but Px okay. This is just divergence of the right, because the Green theorem is the divergence theorem, just in dimension two. Okay, so that's it. We stop here. We will continue review the problems and well, we are gonna have 2 review classes. Just a sample test. I'm not ready yet. I don't have a sample test yet. Gosh, I did not even record it at the end. Sorry.